Hello everyone, welcome back to this online class. My name is Francis Okech and my YouTube channel is Professor Francis Okech. Today we are going to look at Calculus 2 and our main topic is on tabular integration. We need to know what is tabular integration and then we look at some problems involving tabular integration. So let's define tabular integration. Remember, we have looked at several techniques of integration. So when you talk of tabular integration, it is simply a special case. It is a special case of integration by parts. A special case of integration by parts. When do we use it? Remember integration by parts, this rule that we always use, LaTeX. And when it comes to tabular integration, we are going to use it when the function u is a polynomial and dv is either trigonometric or exponential function. So we can write that it is used when u is a polynomial and dv consists of either trigonometric or exponential function. dv consists of either trigonometric or exponential function. Remember, when you talk of integration by parts, you need to integrate a product of two functions. So tabular integration is just a special case of integration by parts. And in this case, our u is a polynomial. Our dv is either trigonometric or exponential function. So I'm going to give you some examples to illustrate how to integrate using a table. So you can write examples. What you need to take note of is that the tabular integration is easier than the integration by parts. So we are asked to evaluate the following. Evaluate part A, the integral of x squared times sine 3x dx. So what you do here is to decide on which function is u and which one is dv. Now look at our functions. This one is a polynomial. It is algebraic. And this other one is it's not trigonometric, but yeah, this is trigonometric because of sine 3x is a trigonometric function. So we said whenever u is a polynomial, which is algebraic, then we use tabular integration. So we are going to say let u to be equal to, of course, we are going to let u and dv over dx to be equal to the other function. So in this case, our u is equals to x squared. Our dv over dx is equals to sine 3x. Remember, it's always dv is equals to sine 3x dx. So I'm making sine 3x the subject. That will be dv over dx. That's why I'm writing dv over dx. Take note that in integration by parts, we always say that u is equals to x squared then you always say that dv is sine 3x dx. So I'm now dividing by dx so that I get sine 3x. So this will be here as the denominator. So dv over dx is equals to sine 3x. Now what you do here, we are now going to differentiate u and integrate the other column. The first column you differentiate until you get to 0. The second column you integrate. So let's start by differentiating x squared. That will give us 2x. When you integrate sine x cubed, what do we get? What gave us sine 3x, I mean, sorry. So it is, when you remember, when you differentiate cosine, you get negative sign. So when I differentiate negative cosine, I will get positive sign. So this will give us negative sign, cosine, I mean, negative cosine of 3x, everything over 3. Now again, continue integrating, differentiating 2x. When you differentiate 2x, we are going to get 2. And now integrate cos 3x over 3. What gave us that? When you differentiate sine, you get negative, you get positive cosine. So here I expect to have negative sine 3x over 9. When you differentiate 2, you get 0. And now when you integrate negative sine 3x over 9, that is the same as cosine of 3x over 27. So what you take note of in tabular integration, you are going to have 2 columns. The first column is u, the other column is dv dx. Now the first column, you differentiate until you get to 0. Then the second column, you obtain the corresponding integrals. Integrate each of those functions in the second column. So once we get to 0 under the u column, we stop there. And so this is what we do next. Now we are going to link these functions, these 2 columns. The x squared will be linked to this one. Remember, I have passed sine 3x. Take note. 2x, you link it to this. 2 will be linked to this. Take note, I have passed 0. I don't need it. Neither do I need sine 3x. The first value in the second column, don't use it. Similarly, don't use the last value in the first column. So look at the way I've linked them. So I'm going to assign them some signs. Here we are going to write a positive. Here we write negative. And here we write positive. In that order. It must be positive, negative, in that order, depending on how many arrows you have. So in this case, we have only 3 arrows. That's why it is positive, negative, then positive. In a case where you had 4 arrows, the other sign will have been negative, etc. So what do those arrows mean? So this is what they mean. That, of course, I'm going to write something on the right-hand side here. It means you take x squared, of course the sign is positive x squared times negative cosine 3x. So our answer, so you can say therefore, the integral of x squared sine 3x dx should now be equal to, the first one is positive x squared times negative cosine 3x over 3. That's the first arrow. The second arrow is negative 2x times negative sine 3x over 9. That's the second arrow. Then the third arrow should be a plus. plus 2 times cosine 3x over 27. And then don't forget to write the constant of integration because this is an indefinite integral. So when we simplify, that should now give us negative 1 over 3 x squared cos 3x plus 2 over 9 x sine 3x, and then I can see plus 2 over 27 cosine of 3x plus a constant c. C is a constant of integration. You see the way this is very simple. If you were to use integration by parts direct, you will have made 3 substitutions. In the first case, u is equals to x squared. Another one, u is equals to 2x. Another one, u is equals to 2. So that will be cumbersome. And so to simplify your work, use tabular integration. Every time you see a polynomial as your function u, then think of tabular integration. It is easier than the integration by parts. I'm going to give you another example. So let us call it part B. Part B, we are asked to evaluate the integral of 2x plus 1. This is cubed times exponential 2x dx. Again, if you look at what we have here, this is algebraic, a polynomial of degree 3. And this is exponential. So automatically, if you look at the LaTeX, algebraic comes before exponential. So that is our u. So we are going to say, let our u, we will have u and another column for dv over dx. So in this case, our u is 2x plus 1. This is cubed. Our dv dx is exponential 2x. So, as usual, we need to differentiate u until we get to 0, then integrate dv over dx to get the corresponding integral. So let's differentiate 2x plus 1 cubed. That will give us, remember, when you use power rule, it will be 3 into 2x plus 1, then times 2. So that is 6 into 2x plus 1. So that will give us 6. Remember, this is squared. 6 into 2x plus 1 squared. What about the integral of exponential 2x? That will give us exponential 2x over 2. Again, differentiate 6 times 2x plus 1 squared. That will give us 24 times 2x plus 1. Integrate exponential 2x over 2. That will give us exponential 2x over 4. Let's differentiate 24 times 2x plus 1. That will give us 48. Integrate exponential 2x over 4. That will give us exponential 2x over 8. And finally, differentiate 48, which is a constant, you get 0. Integrate exponential 2x over 8. That will give us exponential 2x over 16. Very important. Now we link them. We are going to link them. So we start with here. This arrow should point to the second value in the second column. Again, so you proceed in that manner. Another arrow. another arrow, and the last arrow is here. Now in this case, we have how many of them? There are four arrows. Assign the signs starting from positive, negative, positive, negative. I said they should alternate in that order from positive, negative, etc. So now, with this, now we can be able to evaluate our integral. So we say, therefore, the integral of 2x plus 1 cubed times exponential 2x dx. This is the same as, let's start with the first arrow. Remember, I have not used this. Don't use it. Neither have we used this value. So we'll have 2x plus 1 cubed times exponential 2x over 2. The other one is minus 6 2x plus 1 squared exponential 2x over 4. The other one is positive, so plus 24 into 2x plus 1 exponential 2x over 8. And lastly, we have minus 48 times exponential 2x over 16 plus a constant c. And if I simplify this, it can now be written as, you see exponential 2x is common. I can factor that out so that this can be written as 1 over 2 times 2x plus 1 cubed. Minus 6 over 4 is the same as 3 over 2. 2x plus 1 squared. I can see 24 over 8, that is the same as 3, plus 3, 2x plus 1. 48 over 16, again, that is 3, so minus 3. The whole of this is multiplied by exponential 2x, and then there's a constant c of integration. Again, this is very simple. As long as you know how to populate the table, then your work becomes easier. The last one, I want to give you an example where now we have the limits of integration, what we are calling definite integrals. I told you definite integrals are those integrals where you are given the limits of integration. So let's have it as the third example, that is part C. So we'll have part C here. And in this part C, you are asked to evaluate the integral from negative pi to pi, negative pi to pi, of x minus x squared times cosine of nx dx, where n is an integer. N is an integer, either positive or negative, including 0. So if you look at what you are given, this function x minus x squared is algebraic, and the other one is trigonometric. So in this case, our u will be x minus x squared. So this is what we'll have. We're going to say let u, we'll have u, and also another column for dv over dx. So we are going to say let u to be equal to x minus x squared. And the other one will form dv. So that is cosine of nx. So let's differentiate u. Differentiate x minus x squared, you get 1 minus 2x. Integrate cosine nx. What did you differentiate to get cosine? It was sine. So this will give us sine nx over n. Proceed to differentiate u. I'll differentiate u, that will give us negative 2, because 1 is a constant. When you differentiate 1, you get 0. So when you differentiate negative 2x, you get negative 2. Integrate sine nx over n. That is the same as negative cosine of nx over n squared. And finally, integrate differentiate negative 2, that will give us 0 because it is a constant. Integrate negative cosine nx over n squared. Ask yourself, what did you differentiate to get negative cosine? When you differentiate sine, you get cosine. So when you differentiate negative sine, that will give you negative cosine. So here we expect the answer to be negative sine of nx over n cubed. So we now have the table. We now link, let's now link these functions. Remember, these are a bracket. So this will be linked to this. Similarly, here, and lastly, this one. Remember, I have not used this. Neither have I used this one. So I'll give them signs starting from positive, negative, then positive. So when you come back here, we now say that therefore, our integral from negative pi to pi of x minus x squared times cosine of nx dx is now equal to, it is equal to, the first one is x minus x squared. Of course, it is positive, positive x minus x squared times sine of nx over n. Remember, the limits are from negative pi to pi. X is negative pi to x is equals to pi. The other one is where we have the negatives. Remember, this negative and this other negative will cancel, so we'll have positive. So the next is again is positive, because the negative times another negative gives us positive. So 1 minus 2x times cosine of nx over n squared, and again from negative pi to pi. Then the other arrow is positive, positive times negative 2 times another negative. You see, those two negatives again will cancel. Again, the value here is positive. It is positive followed by negative followed by negative. We are multiplying them. The result is positive. So again, plus 2 times sine nx over n cubed from negative pi to pi. A point that you need to take note of is that when you are given a definite integral, then there's no need of writing the constant of integration, because it will still cancel out when you plug in the limits of integration. So that's why I cannot write here plus c, because I know the limits of integration. So let's start by plugging in the upper limit in the first integral, in the first term, I mean. Where there is x, you put pi, so I'll be having this, the first term, is pi minus pi squared, then times sine n pi over n, then minus, with the lower limit where x is negative pi, that will give us negative pi. Remember, what is negative pi? When you square it, you still get pi squared. So minus that one, then times sine of negative n pi over n. That is the first bracket, the first term will give us that. Then we have plus this other one will give us 1 minus 2 pi times cosine of n pi over n squared. Subtract, when I now use the lower limit as negative pi, I'll get 1 plus 2 pi. Remember, it was negative pi where there is x, that's why we have a plus because of negative and another negative. Then times cosine of negative n pi over n squared. That is the second one. And finally, the third term is this. It's also a plus. I can factor out the 2, then bracket sine n pi over n cubed minus sine negative n pi over n cubed. I want us to take note. Take note that sine n pi is the same as negative. Let me write negative sine n pi. This one, sine of negative n pi is the same as negative sine n pi. That's an identity. Another one is cosine of negative n pi is the same as positive cosine of n pi. And that means a sine is an odd function. This is an odd function. This other one is an even function, Also, you need also to take note of what do you get when you have cos n pi and also sine n pi. So also, you need to take note that sine n pi will always give you 0, where n is an integer. Cosine, that should be cosine of n pi will always give you -1 raised to n. Again, here n is an integer. For instance, when n is 2, that is cos 2 pi. 2 pi is 360 degrees. Cosine of 360 degrees, that is 1. When n is 1, we talk of cos pi. Pi is 180 degrees. Cosine of 180 degrees is -1, etc. So these identities are very, very important to help us simplify what we have in our solution. These ones and also this and this. So now let's go back. Let's go back here and simplify this. Wherever you see sine n pi or sign of negative n pi, those ones are zeros. They are zeros. So where we have sign, this will be 0, they'll vanish. Even this will vanish. Everywhere you have a sign, just note that they will vanish. So we only remain with the cosine. So therefore, I can extend this, extend it, so that when we work out this, we now remain with the answer to be equal to, and remember, cos n pi is the same as cosine of negative n pi, so that can be factored out. So cos n pi over n squared is common, so we'll write this as cosine of n pi over n squared is common, so that in the first one we have 1 minus 2 pi, and then the other one is minus, it is this one, minus 1 plus 2 pi. So that what will we get? And remember, cos n pi is the same as negative 1 raised to n. So this will give us negative 1 raised to n over n squared times 1 minus 2 pi minus 1 minus 2 pi. And you see this can be simplified. 1 minus 1, that is 0. And so this can give us equal to, here we'll have negative 4 pi, this and this. So we'll have negative 4 pi times negative 1 raised to n over n squared. So that is our answer. Negative 4 pi times negative 1 raised to n over n squared. That's the answer. So you can just say that therefore, that integral, I can just conclude here, and you say that therefore, the integral from negative pi to pi over x minus x squared times cosine of nx dx should be able to give us negative 4 pi, negative 1 raised to n, and this is divided by n squared. So those are some examples, some of the examples that you may encounter when it comes to tabular integration. And you can see the process is very, very simple as compared to integration by parts. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, to like, and also to share this video. When we meet next time, we look at other techniques of integration. Bye-bye.